And therefore, I think it's not necessary for the Finnish people in this audience to introduce Professor Mustonen, but to do it for the rest of the audience. I will tell you in short an old German tale. The hare, always claiming to be the best runner, was once challenged by a hedgehog. After quarreling for some time, it was at last decided to settle the question on an empirical basis. The long rows of a potato field were chosen as their sporting ground, and off they went. When the hare reached the end of his row, he heard the hedgehog say, "I am already here." So they turned for a second try, and again the hare was welcomed by the hedgehogs saying, "I am already here." The hare asked for more, and again he was faced with the stable outcome, "I am already here." So what has this story to do with Professor Mustonen? Nowadays, the hare changed the profession. He is a statistical software producer. And if you look at all those advertisements, you always hear him say, "I am the best." The hedgehog nowadays is called Seppo. But I think there are two essential differences. You never hear him say, "I am already here." So let me do it for him. And I want to stress that many of the ideas we in the statistical computing community talk about were long before thought and mostly worked out by Professor Mustonen. And the second essential difference is the hedgehog in that tale, he cheated. He placed his wife on the other end of the row and let her say this sentence. And I can assure you that Professor Mustonen really was there. So I think let's hear this day where he stands and what the hares will tell us what we have to think next years. Thank you.
Thank you, Mr. Chairman. Ladies and gentlemen, I have to make some preparations before starting because I like to sit at my instrument. And also I have to take some. I hope that everybody can see something there, because my presentation is strongly dependent on visibility of this screen. So please, if somebody cannot see their back, please come closer. There are, I think, empty places. I like to go to the point, and I clear the screen, and I'm not going to give any formal presentation. I don't like to speak about general aspects of my approach, which is called editorial approach. I write it. Okay, of course I made mistakes, but I'm very clumsy at the keyboard. You'll see many. And now in connection of statistical computing. As you see, I can type any text in this screen. And when I can use Finnish, I'm pretty quicker. So, however, I like to do that in English and as well, and I have some assistants here. I have ready-made tutorials made on this system, but I am using them later when after presenting some smaller examples by hand. As you see, I can type any text on the screen. It's like a text processor. But as well, I can also type numbers. And if I have some addition there and this equal sign before the cursor, I can activate this, and I get the result immediately after the equal sign, and I can continue typing. Also, I can, of course, edit this plus to a multiplication sign and activate this again. I get a new number, hopefully correct, and I can continue. Then I can also give notations to my numbers. I can have notation that A is equal to B plus 1. And somewhere else, I can make extra lines there. I can type some Finnish again, and then B equal to 3, and some important things again, and then perhaps C, I say that it is equal to square root of A times A plus B times B. Okay, and then I can go to any place here. And now I'm interested in what is C plus 1. I activate this and I get 6. And what's the idea? It's the same as with people who see some text. If you were asked to compute what is C plus 1, you would be interested in what is C, and you try to find it. You find that it's square root of this expression, and then you need A, and you find somewhere there on this line that A is equal to B plus 1, and then you need B, and you find it on the line 8, and after that you know B is 3, and then A is 4, and then C is, okay, it's 5, and then C plus 1 is 6. But of course the system does it very rapidly, so that you see practically no time to reach the result. And I still can continue typing. Now I go to more serious applications. I put a border between this and the next example. I am taking a risk when using this kind of system with so many people present, and this is some kind of excuse. I write down a level of demonstrations. And it says the probability of a successful demonstration is, I have a well-known formula for it. It's P, or it's a function of two variables, T and N. And this is by definition the logarithm of T plus square root of N. I need one. Okay. Where T obviously is the time in hours, and N is the number of people present. So here we have N equal to, there is I think there's 250 places here, and I had to take a look. Okay, there's 70% crowding, so that it's this times this. You can compute the actual number if you like, or I can show it. It is, of course, 175, my estimate. But I can cancel it, okay, well, perhaps I write it correctly here we have, and t equal, I have only, I think I have 24 minutes for my, okay, it's so that it is,
and 2 more from Tampere.
2 more for Tampere, okay, so I corrected, okay, I put 26 then, but this does not increase my chances, divided by 60. So, what is P T N? Oh. So, I had the wrong expression here. It should be exponential. And there should be minus. You see, the demonstration effect is already present. Okay, this was my. Nobody said nothing before I got the this is the correct value. You see, this is not the statistical law because there are no parameters to be estimated and no error term at all, so that it's true. It's true. Of course, you see that it's correct because if I start by if there are no time and no people present, it's 1, so that as expected. And of course, if I am alone and spend the same time, t denoted above, I think it's reasonable. So that this is my excuse. And I take no responsibility anymore about success of this, but I still try to continue. I now take some statistical functions which I'm going to use later, at least some of them. I have functions related to normal distribution. For instance, the density function of standard normal distribution, the parameters 0 and 1. If we take the value 0, it is, you see, this value, which is same as, you know, it is 1 divided by square root of 2 times pi. If I like to ask it, it gives an error message because it does not know what is pi, so that I have to teach it and tell that pi is 3 point. Perhaps this is accurate enough and you get approximated. Perhaps I have some decimals not correct, but you see, that's the situation. And of course I have another function with big F, a capital F, with the same parameters. Or I take the value 2, and we see that we get this a typical value for the standard normal distribution function. And we have also its inverse. The notation is now n full stop g. And if I take something which is around the previous value of the distribution function itself, oh no, it was 7725 approximately, I can get this value. But I have another shorter notation for the last one, as I call probit, and with the same argument. It does not give exactly the same value, but something rather near, because this is quicker in computations. I like to use it. I also introduce a random function, as in BASIC we have RND function, and when we take it with the argument 0, every time it gives a different value. And now we can combine this with the probit function. And you guess what's happening actually. We get standard normal deviates every time when we activate it. Now I'd like to make a small simulation experiment, and I think that we have a human population where we have the weight of a human being, and we could state that in centimeters that it's 175 plus 10 times an error term, which is, I call it epsilon. And I take this here and define that epsilon is this one. I try to erase this. You see, we have now this kind of situation. I move this upwards. And now we can ask values of weight this way. Similarly, we can define the height as, let's say, 25 plus 7 times.
I think you've got the H and the W the wrong way round. They're going to be very short and very broad.
Oh. And I define a similar I took some copies of the EPS definition there, and define also EPS2 in the similar way, so that when I like to know values for height, I can have this kind of values. Now I can activate them simultaneously by putting an extra full stop after this. And now you see, when I activate this, I get the pairs of values. But this is not very realistic, because there is now zero correlation between height and weight. And therefore, I have to make some adjustment. And you know, there are various ways to proceed. I can abandon the old definitions of EPS. Instead, I take some random variables u1 and u2, and then define, let's say, EPS equal to u1, and then EPS2 equal to r times u1 plus square root of 1 minus r times r, and this times u2. And then r represents the correlation between height and weight, so that we can select certain value, let's say 0.67 for correlation. And now it should give values which are correlating with the correlation coefficient of 0.67. Now I like to generate a sample of these values by first generating a file for the coming observations. And I can present the data sets freely on the screen as well as a list or tables. But for bigger samples, like here, I like to generate a sample of 300 observations from height and weight variables with this correlation. I like to create a file first. And start by the file create operation. I call the file sample 1, and I am going to make two variables there. They are both will be numeric variables of a certain time. For this is technical. And second, it was called height, and this was called weight, and there I put an end there. And now I activate this in order to have, okay, there's one line missing telling that there can be and I initiate this file by 300 missing observations or empty observations. And now I can generate the actual variables very easily by putting a variable operation xy and saying that they are going to sample 1. And now when I activate it, this was not x and y, this should be, of course, height and weight. So you can see the values typed. And I don't know, these are not the values, they are indices of the observations. We can follow the computation. And it is an interpretative process. The system has to read, for each observation, it has to read what the definition of height and weight, and therefore it takes some time. But when we have the sample, we can use it. For instance, we can make a plot of the G-plot sample 1 and variables and when I activate this, I'm sorry I cannot use the best resolution on the screen, but you see the idea. It's fully automatic with the scaling, but I can give the scales as well. If I like to see the correlations, the moments, mean standard deviations and correlations, I can use, for instance, core operations and refer to sample 1. And I mention one extra line, let's say 54, the next line for the result, so that if I activate this, you have the values here. But now there's something wrong, because you see there are some, okay, they were, I already used x and y, and they are now nonsense. But you see the height and weight variables, they should have, for instance, they have their means there, which are, I think, reasonable. And also the standard deviations are there, and their correlation is there. But x and y, I tried to generate x and y without the definitions, but they were already created into the file, so that they are nonsense and what there happens to be. But for those actual variables, I think the situation is correct. There you see that my probability in the beginning was right indeed. Now I try to conclude my presentation by giving one example with a ready-made tutorial. And perhaps if somebody still likes to ask about this, I save this with a certain name on the disk so that I can take all this story into use later. And perhaps I take a new fresh start to the system. This is the normal way to start with this system. And I select here, there are some instructions for a beginner. I select here some items. I go straight to a tutor called Circle. And now it's completely automatic. I can stop this demonstration by pressing any key. Now it's starting by making some preliminary checks with the screen. It tries to find suitable scalings because I cannot use the best possible resolution. I can stop at any point by pressing some key and read carefully what's there. I'd like to make even here an artificial sample, but now from points which are roughly on the circumference of a circle. And this sample will also include an outlier, and we shall investigate its influence in the parameter estimation. Now starting generating the sample, I go to the same style I were using in the previous example. It's telling the rules for x and y, and the correct values for the radius r, it's 3, and the coordinates of the center, they are 5 and 7. While it's running, I can perhaps point to certain points there. This is now like a ghost user operating the system. Originally, this story has been generated simply by using the system and letting the system to save all the keystrokes to a certain file. And now actually I activated this file, and this ghost user is now operating. Now it's using, just used the var operation there and generated now 40 observations to a file called Circle. And when I activated this, it had to find x. Its equation is there, and y similarly is there. And they are both depending on 3 parameters, y0, x0, and r, and also t. And I assume now that t is uniformly distributed around the circle, and then there are also 2 error terms, EPS1 and EPS2, which are normally distributed, and their distribution law is explained there. So that this var operation actually reads this information and uses it when generating these observations. And it should now plot the sample by activating this gplot operation there, and you see the circle. Then it goes further and makes a replacement with a very odd observation, x equal to 10 and y 11. It makes that alteration there and plots the sample again to see what kind of outlier it is. Of course, it's a very distant observation, and of course in practice we should reject it and do the estimation without it. Now we forget the true values of parameters and try to estimate them from the sample generated above. And we start from very poor, very bad starting values. And here comes now the plot giving the circle with those bad initial values. We have the sample there, and there is the initial value for the circle. Then in our system we have a special, or rather general, estimating operation where we can give the model in this form. you see that it's like a regression model without an error term, which is implicitly supposed. But it's funny that there is parameters to be estimated on both sides. This R is to be estimated, and as well y0 and x0. And this estimate operation needs the data set and then a model defined there. And now it's an iterative process because it's a nonlinear estimation problem. And after now 9 iterations, it gives the result. I may remark that each time when I run this, the values are different because the random number generator is time dependent, so that there might be surprises also in that way. Now we have the estimated circle here, and you can see that there are several points here inside of the circle and here outside the circle, so that there is certain drift caused by this outlier in ordinary least squares estimation. And it's natural to try to improve by using a more robust estimation criterion. And I'm using the MAD criterion, or L1 norm. And then we are using also the ordinary least square estimates as initial values. We state that new criterion by this line, criterion equals to L1. And now when we have no derivatives available, actually the estimate operation, when possible, makes the analytic derivatives of the model function with respect to parameters, and then we can use more refined methods. But here we have to use very simple search method for finding the estimates. But when we have good starting values, we can reach the optimum rather easily. I think it's now coming to the end. I run and I can stop my talk. But if you like to see more, I have a presentation in the hall and sitting there at a similar computer so that we can discuss more about these problems. Thank you.
Thank you.